Thank you very much. So we can see it perfectly well. So, so our next talk is by Barak Saki. So thank you very much, and the floor is yours.
Hello. So my talk is about detecting gravitational waves using the public LIGO VIRGO data. I am from the Weizmann Institute of Science. I recently started my job as a new principal investigator here. I'm obliged, because of my young age, I'm obliged to tell you a little bit about myself. So my main tools are algorithms and statistical methods with the goal of making new discoveries. As you probably know, because cosmology is famous for this, in every modern project in astronomy and astrophysics in general, data analysis plays a key role, and that improvements in data analysis are something that improves the community across the board. One example of something that I've done in my PhD is the algorithm for detecting transients. So detecting transients is something that is very, it seems like obvious, okay, there's a new source, so just, take the previous image and the past image and subtract them. But the problem is that it leads to artifact, and there were many problems requiring human candidate scanning, and it interfered with science. And in the end, the problem was actually that the equations were wrong, some assumptions about the data were not correct. And once you put inside all the components in a statistically rigorous way, you find a way to perfectly subtract the images, and the false positives are gone. And as a bonus, you found also 20 to 50% more survey speed. So more examples like this are for image addition, actually very relevant for cosmology, and to the best of my knowledge, not implemented anywhere. Something about detecting FRBs, which is probably going to be mentioned in, well, FRBs will be mentioned in Kendrick's talk. I will not talk about this more here. And also fast parameter estimation for gravitational waves, which I will not talk about in this talk, but this is the real project that got us into the gravitational wave business. So why am I telling you this? Because I'm hiring, and I have many exciting projects, and I really hope that someone in the crowd will propagate this to fantastic PhD students or postdocs. So just in the titles, detecting pulsars in binary systems is something that is not really well known how to do, and I have a very promising way to do this, and to increase the sensitivity for detecting pulsars in binary systems in a substantial way, and perhaps leading to a much more sensitive search for neutron star black hole binaries in the galaxy. Also, many important questions about FRBs. For example, are FRBs periodic? Periodic not in terms of long periodicity, but millisecond periodicity. So there's a method to do this, and I'm hiring people, and I hope that some people are going to help me with this. And also in gravitational waves, we have several projects. One of them is tackling the important problem of reducing the technical noise from advanced LIGO data. So I'm hiring. So without further ado, let's talk about the main event, detecting gravitational waves, which is a project that I've done with my colleagues at the Institute for Advanced Study, and now all over the world, because Liang Dai is now in Berkeley, and Teja Srivenumadar is now in UCLA, and I moved to Weizmann, and Matthias and Horchen are from Princeton, and I recently hired a student to help me with this, which is Jonathan Mushkin, bold in the. Okay, so where were we? So as the previous talk presented, there were 10 binary black holes detected in GWTC1, and one neutron star merger along with its EM counterparts, which I consider one of the greatest achievements of astronomy in the last few decades. We, as in the IAS team, have constructed an independent pipeline and discovered additional 8 binary black holes in O1 and O2. We are currently working on O3. This was only very recently, like 24 days ago, published, so it will take a little bit more time. We also worked like everywhere on like all over the field in gravitational wave data analysis. So, for example, analyzing the populations of binary black holes led by Javier Ule, and a lensing search that was led by Liang and me. We do not operate in vacuum, so some of the methods that we have developed have been adopted by LVC for the new searches, especially the PyCVC version of the searches adopted a few of our methods. And we are currently working through the data with full force of our methods and maybe developing new ones. And we also analyze the sets of O3A detections. So we have some population analysis of O3A that is published just today, and a possible detection of precession in GW151226, which was published this week. Okay, so a little bit of introduction to merging compact objects in string data. So we have some data model. So what is this plot? There's the sensitivity of the detector, the function of frequency. This is a log-log plot, so something that is very high here is actually orders of magnitude higher in power than the floor that it sits over. So these lines, this high dynamic range in the power spectrum makes the analysis of gravitational waves a little bit more cumbersome than you would think, like naively, if you see the O4 design or O3 design curves. Moreover, nobody tells you what is this power spectral density. So these lines probably are known to a person that constructed a detector. Probably almost every line has its own story. This is from which hardware component. But some of the things that are a little bit more bumpy, those are actually unknown. Nobody knows how to explain them. Some people have guesses, some do not, and we as an external group have no guess to do this. And also this is time variable, so you have to measure this with the data itself. There's no exit to, nobody can tell you what is the power spectral density to a few % precision without the data itself. So the signal model, you probably heard too much about already, but I'll just say that it consists of some intrinsic parameters like total mass, mass ratio, and effective spin, and maybe some in-plane spins and tidal deformability. This creates a waveform. This waveform needs to arrive from some place in the sky. So you have the extrinsic parameters of distance and sky position and orbital orientation. And after all this thing, you have like a template. You have a prediction of what GR with these parameters would impinge on the detector. And then you have to detect it. So in order to detect it, you have to use Fourier domain match filtering. So if you have noise, and the noise has a power spectrum that is non-trivial, then you have to do, when you analyze like the super, when you take the detection problem, you can from first principles prove that the most sensitive detection statistic is the matched filter with this formula. So let's understand what's in here. So we are summing over frequency, okay? And this is the data at a particular frequency. And each piece of data, each frequency, each number, okay, is weighted by the response to the gravitational wave. So how much gravitational wave will you see in this particular number, okay? Complex conjugate just in order to match the sign. And you divide by the variance. So it's inverse variance weighting and matching with the template, okay? And usually people present only this formula, but actually the full formula has a division by this scalar. Okay, so usually people push this into the template and they say that the template is such that this number is 1. But it's very important to put this in the formula, because you will see, as you will see further into this talk, when the power spectral density is unknown, the first order error in the power spectral density is actually entering through this term. So just bear in mind that it's actually important to write this normalization. Okay, so we know how to match one single template. How do we do with a population? You know, there's a continuous parameter space. So obviously we cannot enumerate a continuous parameter space, so we have to use some approximation. So the first approximation is that we say two templates are similar if by using one I can detect the other in the data. Okay, and by detect I means that I can recover more than 97% of the SNR. Okay, so this is a very conservative similarity condition. Okay, and it guarantees that every physical waveform is represented. So every physical waveform, if you put it in the data, then there would be a template that is at least 97% close, and therefore your bank is complete. Okay, because you will detect every physical waveform that happens. What will you do? Then you take every template in the finite bank that represents the continuous phase space, and you cross-correlate it with the data from all other detectors. And times in which scores are very high, you call them triggers. This is some particle physics jargon. Basically, it's times in which there's any chance in which there's a gravitational wave. Okay. But we have several detectors. So these detectors are located on the Earth. So between two LIGO detectors, there's a time delay of 10 milliseconds. Okay, with Virgo it's 20. Doesn't matter that much. And you can do several things. One of them is to sum incoherently the scores from different detectors. So this is literally saying, I believe the amplitude and phase in each of the detectors and the arrival time are just independent variables. Okay, this is an approximation. It's not really correct. Okay, and there's but after you make this approximation, then the score is just, you know, you add the best from Hanford and the best from Livingston, and you move on with life. And there's coherent detection in which the detectors are. So LIGO and Hanford are nearly the same in 3D. So we know that the phases and responses of the LIGO detectors are expected to be close, and also the configuration of Virgo is also not random. So not every configuration can happen, and you have to integrate over all of this. When is this important to use some coherent instead of incoherent detection? When the detectors are not very symmetric in response, and when the event is near the detection bar. Okay, so that you really need to squeeze the last bit of information you can find. Okay, so how do you compute false alarm rate? So actually you can exactly measure the background of any search you are doing if you have multiple detectors, because you can take the different detectors and you can shift them by some unphysical time and repeat your analysis. And if you find something when there's an unphysical time delay between the detectors, it means that you have a bug. Or put it the other way around, you can use many different time slides in order to make a histogram of what do you expect by something which is not related to astrophysics, by just a regular detector noise, but with all the complications that are not modeled by assuming that the detector is Gaussian noise. An important caveat to this is that this is relevant when the signal in question is not hinging only on one detector to be declared as a real event. This is because whatever time slides you are doing, if only one detector saw the event in a sensitive way, then you cannot get any estimation of what is the background at this level, and you'll have to use some model. And I wish to thank the LIGO collaboration for enforcing this standard, at least at the beginning, because this is a wonderful tool that keeps you honest. So, when people cheat with statistics, usually the first person they cheat is themselves, and this prevents that. So in my view, this is something that should be used across the board in astrophysics. Now, after you found an event, yay, gravitational waves exist, you still have to say something about astrophysics, and in order to say something about astrophysics, you have to measure the parameters of the events. And this seems like some easy task, but it is not. So in order to do this, first of all, you at the beginning to the gravitational wave parameter estimation, you have to believe that the detector noise was Gaussian for this particular restricted time, because otherwise hell breaks loose. And you define some prior distribution of the physical parameters. This is very natural when you are talking about the orientation in the sky and the orbital phase of the binary. But this is actually very unnatural when you care about parameters like spin and masses, because those don't have a natural prior. You have to come with some astrophysical insight of what should be this prior, and it actually leads to problems. So after you assumed your prior, you sample the posterior. This, sampling the posterior is something always to be done with a black box, and debugging these black boxes is very hard. But in the end, it is possible to measure parameters of gravitational wave mergers, and we do it. So all of what I said now was done by the LIGO collaboration even at 2015 almost. The coherence score is only in the GWTC1, I believe. So why do we open the project in July 2018? Okay, so we just could not square what's going on with the numbers. Okay, so allegedly, at the time of that we started the project, there was some gravitational wave event, GW151012, with SNR of 10, actually slightly more than 10. Okay, and it was declared as a barely detected. And we did some back of the envelope computation, and we said, okay, in order for this to be barely detected, there should be 1 trillion templates. And we read the paper, and there's like 100,000 templates, and that's if you include things that are not binary black holes, that are binary neutron star also. So what's going on? We couldn't answer this question, and we also said, okay, so maybe it is some kind of glitch that passes the older net, okay? But then the inferred glitch rate is 1 per few seconds in order to do this. In order for this SNR to be the limiting thing, you should have some glitch rate of 1 per few seconds in order to beat. So this event is also SNR 7 for each of the events. And SNR 7 is something common, and if you have a glitch every few seconds, then you can overproduce this kind of things. But again, this is not something that happens. If you look at the tables from the paper, then it's a few per hour or few per minute, depending on which run and and how bad is it at the moment. But few per hour is the standard number. So we knew that glitches could not be the full story. And also we said, okay, if glitches are so important, why is there only one test that the LIGO collaboration is doing in order to remove glitches? And this test itself is unsafe to pure Gaussian noise. So we said, okay, we have to open this project. How did I open this? So we came open-minded to the project and we said, okay, fine, let's start with a few weeks of a trial and see if we can analyze a few hours of data and get some perfect result, and perhaps we'll understand what's the issue. And we did it, and after a few weeks, lo and behold, we did not understand what's the issue. So we have decided to open a project on how to detect binary black holes. At this point in time, it was just me and Teja. And we decided not to look further on what LIGO or anybody else were doing, and just reflect on every decision we make from first principles, so that we know that we are not going to make the same mistakes, because the easiest way to make the same mistake someone else was doing is to read what he was doing before thinking. So you have to first think, then read. So a few of the things that we found that we have to change is to change the template prior. Okay, so we use the template prior that is flat in log mass. Okay, and this itself gives you some 30% more volume for binary black holes. We also found out that when people say S and R, actually this has two components: the S and the noise, the S and the N. And it turns out that there's a problem measuring the power spectral density, and this problem of measuring the power spectral density can really affect your ability to detect binary black holes and binary neutron stars. So each one of those was granted some 30% boost in volume by correcting this effect. And we also had, revised and from first principle, not from first principle, so from, without looking at prior art, we decided how to deal with marking bad data and how to veto out any particular signal that is not a gravitational wave, but is something that a gravitational wave template would ring on. Okay, so we found a way to mask data and to look at candidates in a very fresh way with several tests. And here again, measuring the contribution of this is about myself. This is not with respect to LIGO. So I know that if I use this veto, then I get at least 20%. Here it's like zero, it's written 0%, but actually what's happening is that I cannot run the data without aggressive data. I cannot run my pipeline without aggressive masking of bad data. And in order to be aggressive, we had to devise a way to in-paint data. I will talk about this in a few slides. We also found a way to incoherently add two detectors in a way that is more sensitive than regular addition if you have residual glitches. And we treated the results even more carefully at the place in which we know that one of the detectors got a substantially higher response than the other. And about 10 to 20% of the events should be in this region because of different sky orientation. So the different detectors are oriented differently in 3D, and there are places in the sky in which let's say the Livingston detector would have a favorable response, but the Hanford one would not have. And because the Livingston detector is already a little bit more sensitive, then you get some disparity that is so large that actually you are going to miss the event altogether in Hanford, but see it in Livingston. And the total is about a factor of 2 in volume. This is well measured both in an injection study and in the practical way of saying that we actually found twice more events in O2. And this is equivalent, so if you want to work out what this means in order of rejection of the background, this is 4 to 5 orders of magnitude. So this is, we are really peering deep into the rabbit hole. So we've done this injection study, And lo and behold, more than 50% of the events we are finding at an SNR that is approximately 70. And even some of these blue guys, so you see this, so in this particular region in which one detector is more sensitive than the other, okay, in this particular region, we also have a dedicated pipeline to find all of this. So, yeah, so this is for the methods, but you're not here for the methods. So let's talk about, well, that's not the end of the method, sorry. So let's talk about this prior. So I have 5 minutes, that's what you're saying. Okay, so let's skip with the methods and move on with life. So what are the science cases to do with the binary black holes? So first of all, there are many theories of how to form binary black holes. The leading families are dynamic formation and binary stellar evolution. And we have some cross things that should not be violated, better not be violated by the data, like an upper mass gap due to some supernova pair instability, or maybe a lower mass gap because we think we understand something about core collapse supernova. It turns out both of these are, completely crossed out by GW15 in 1905-21 for the upper mass gap, and the lower mass gap, I just forgot the telephone number from now. But it turns out that we can also rule out isotropic spin as the main mechanism for detecting binary black holes. So first of all, what are the signals we have discovered that LIGO have missed? So one of them is the most sure signal we found. Basically, it's a real signal and verified by another independent group. And it has a negative chi-effective, so you might say, maybe it's dynamic formation. There's another one that with my observer hat on, I had to report, but with my theory hat on, I don't know what to do with this negative spin and very small p astro, so I prefer to believe it's not real. But we also have discovered something with almost maximal spin. And it turns out when the spin is high, you have to ask what was the prior in which the thing was analyzed, because the usual prior LIGO is using has an actual zero at maximal spin. And if we ever want to challenge GR at very high spin, then we should at least know that something has very high spin. So for example, if you analyze this event with the LIGO prior, you would see, it's a moderate half spin. But if you analyze it with a flat in chi-effective prior, you see that the data actually talks about maximal spin. Okay, so this is something to watch out. And also we had the first early bird of high masses. So we could say that pair instability is not at 40 solar masses, because we saw some event with M1 that is much more than 40. Okay. Now let's talk also about how to report some results. So if you look at LIGO papers and you ask for some rate, then usually these rates are not very well constrained. And there's a very good reason. It's because the rate is dominated by the super light binary black holes. But the actual events that you are detecting are at the heavy side. So the uncertainties in the rate are actually dominated by the fact that you assume it's a power law, or what is the power of the power law. And actually, if you restrict the rate to some mass range, then suddenly you have a dramatically better rate. And I think theorists discussing the rate about binary black holes should use the confined rate to some mass range. Also, I think it's more honest, because I don't believe that there's going to be a single mechanism that's going to be dominant over the entire mass range. This sounds to me a little bit impossible. So here is a diagram that currently you can't say anything super intelligent based on it. So it's mass versus effective spin. But I do believe that different scenarios for creating binary black holes are going to show different features in this particular two-dimensional map. And as I said, I don't believe that mass range is going to be so democratic that there's going to be one formation mechanism dominating everything. And in fact, as the previous talk said, there's already evidence that there's at least one more, at least more than one power law, because the power law is just inconsistent with the data. But I want to urge caution to everybody, because whatever conclusion you are making from these hierarchical Bayesian models assumes that the correct solution is in one of the spectrum of the things that a hierarchical Bayesian model can do. Hierarchical Bayesian model that they were used, the parameter space that they were used had the correct solution inside. So for example, if spin depends on mass and your model has a product distribution of spins and masses, then you're not going to decide on any true thing in the parameter estimation. So I advocate that when we go to hundreds and thousands of binary black holes, we move to histograms, because HR diagrams are much more readable for humans than Bayesian analysis in top of the Mount Everest, looking at probabilities for these models. Good. So why am I saying that we can rule out dynamic formation? First of all, rule out, what do I mean? I mean that it's not 100% of the signals, okay? That it's not the majority of the signals. So for example, when you have, I understand. So when you have the effective spin, okay, then dynamic formation means that positive and negative spin are going to have the same prevalence. But if you look at this distribution and you just put a Gaussian through it, you can see that there's no excess of negative effective spins, even with the one that we found. While on the positive side, there's lots and lots and lots of signals that you cannot explain by some spin zero distribution. And even when you weight the signals by their luminosity distance, you still see that there's an excess in positive and no excess in negative. So this means that we have no evidence for any negative spin event, and there's no reason to believe we have some. Okay, this is a little bit more technical, but so let's just skip this. Okay, so in this part of the talk, I wanted to talk about lensing, but I see that there would not be enough time for this. So let's just state my final take about the possible lensed event is that it's possible. It's very puzzling. We have positive evidence that there's a lensed gravitational wave because the 1701, 04, and 08, 14 are simply too similar to be in the same catalog. And also they found a friend, they found another signal. But the expected rate is very small, so this is one bad point. But the even worse point is that if you analyze the image types of these lensed events, then you can see that it requires images with a maximum of the lensing potential, which is something that is very, very, very rare and requires fine-tuning. So we just put it out in the community in the hope that at some point people would try to search for this system, because if this system is correct, it has to be some cluster or galaxy group that is doing the lensing. So there's actually hope to find the counterpart. And that's it.
Thank you very much. Sorry, I pushed you a bit at the end. Are there any questions, please? Please raise your hand. Anyone?
I have a question, but maybe we should, since this can be done now in the discussion session, maybe we can move along to the discussion session, and then Ed can take over and we can ask the questions.
Okay, very good. So let's thank Barak again. This very nice talk. Thank you. And Ed, you want to